how did people do on getting those rotation matrices entered?
Tried, but I don't know if it's right.
Okay.
Because I went back into the gallery late and
We're going to, so in this coordinate system, our stress tensor is going to be 5, 0, -1, 0, 10, 0, -1, 0, 2 megapascals. And we're going to do two things. First, we're going to just think through. So we're not going to calculate this. We're just going to think, what's the stress tensor in the coordinate system where x is up, y is to the left, and z is towards us. Okay, and then we're going to calculate it using rotation matrix, and they better match or I'm out of here. I'm done with this. Yeah, exactly. I've had enough today. See, you weren't in dynamics, but I've had enough. Okay, so calculate. The same transformation.
It would be -90, right?
The coordinate system, right-hand rule, so it would be positive, right? +90. Because we're starting at this one, and we're rotating this way.
Are we rotating this way?
We're rotating x up to where y is and y down to where -x is.
Oh, yeah, because it's the coordinate system.
Yeah. Okay, so how are we going to think through this? Well, remember that stress tensors always have you can always draw out the stress cube for a given stress tensor. Okay, so let's draw out the stress cube for this. So we have +5 for the xx, 0 for the y on the x face, and -1 for the z. So I'll put that as +1 and put it in the -z direction. And that means we have 1 going this way. And then for y, we have 10 going this way. And then for z, we have just 2 coming out. Okay, so this is the stress tensor in this coordinate system. That's the stress cube that represents that stress tensor. Okay, so now we have to think about what it means to the stress cube to choose a new coordinate system, okay? The stress cube, I mean, we always just draw it like this because generally speaking, it's so hard to try to draw it in whatever configuration you're really in. But really, the stress cube for a coordinate system always represents, like the faces, the names of the faces are always the axis that's coming out of the face, alien style from the middle, So that's why this is the x face, this is the y face, and the z face, okay? So what does it mean if we rotate that coordinate system? Well, now we're just going to go to, since I chose a very well-behaved transformation of coordinate systems. Now we're going to a case where x is this way, y is this way, and z is this way. And the cube looks the same because the orientation of the faces has to be like this for those to come out alien style. Okay, but now they have different names. Like the top face now is the X face. The obscured face on the left is the positive Y, which means what we're looking at is the negative Y face. And the Z is still the same. Are you with me on that? Okay, well, if we're representing this in this new coordinate system, nothing's physically changed. All we've done is rename the faces, okay? So for it to be the same state of stress, these values all have to be the same. Like, what does this look like? I mean, it looks exactly like this. There's a 10 going this way, a 5 going this way, a 1 going this way, a 1 going this way, a 2 going this way. Okay? For it to be the same state of stress, if the faces are all aligned the same, it has to look the same. Okay? The difference is now these have different names. Okay? So now let's think about the names of the elements of this stress tensor. What's the name of that 10? What element is that?
X.
That's the XX. Are you with me on that? Everyone look at that and make sense out of that. So now it goes 10, and then we don't have anything else on the X face. Now we'll go to the Y face, which is, okay, now this is sort of the tricky one, because what we're looking at here is not the Y face, it's the negative Y. But what that means is the positive Y is opposite of all of these. Okay? So what's the y element?
-5.
-5. Are you with me on that? Because all you do is look at this. This is in the positive y direction. That means on the opposite face, it has to be in the negative y direction. So we have a -5 here. This one's 0. And then this is in the negative z direction, which means on the opposite face, it has to be in the positive z direction. And then for z, we have nothing in the x direction. We have this 1 in the direction of positive y. And we have 2 for z.
So could you also just, I mean, like, so if you rotate the coordinate system one way, could you also just rotate all the vectors the other way and then draw the cube in the same coordinate system?
No, because all you're doing there is
like, instead of renaming the faces, looking at it in the same orientation.
Yeah.
But like rotating.
Remember that what that transformation has to do is it has to change the meanings of the faces with one rotation, and then it has to transform the new traction vectors into the new coordinate system. So you would have to do it in 2 steps.
Sure, but I guess I just mean in this like intuitive way.
Yeah.
Like wouldn't just turning all those like
No.
rotating them around that do the same thing?
Maybe. I don't know. I'm done thinking about it.
Because the y is in the negative x direction.
Yeah.
Wouldn't the arrow on the other face be pointing towards the positive?
Towards the positive. Yes.
Yeah.
Yes. I thought about that wrong. Yes, that's a very good point. Okay, let's think about this again. So this 5 on the negative y face is going in the negative y direction.
Yeah.
So yes, this should be positive. Thank you.
When I
You
did
are
that-
right.
When I did the math in my calculator, it's like everything was right except for that 5.
Oh, okay.
So, yeah, like,
Okay, well, there you go.
So you're just rotating the coordinates 90 degrees.
That's what we're gonna do now is with the rotation matrices is we're gonna do a transformation where we rotate about the z-axis, positive 90 degrees.
Okay, because I thought for a second these were like the negative x and y and z faces for a second.
Okay,
Like, and it's not right, this cube, like we didn't
Right.
flip it to the backside.
right.
We're just flipping the coordinates.
We're right. The cube hasn't changed in this case. I mean, in general, the cube would have to change too, but because these are 90-degree rotations, the cube didn't change at all. All that changed was the meanings.
Okay.
Yeah. So now, any other questions about that? Yeah, so good pickup with that positive.
yeah, so because we're looking at the negative y face, is that one vector, along the z-axis? Is that positive because it's on the negative y face, even though it's pointing in the negative z direction?
It's pointing in the negative z over here, and then since the positive y face is what we really want, we know that on the other side it's in the opposite direction.
Okay.
Okay, so our rotation matrix Q is well, let me draw what I always draw. So we're going from this to this. And that requires a positive 90-degree rotation about z. And so now we can figure out our rotation matrix. Q is cosine 90, sine 90, 0, negative sine 90, cosine 90, 0, 0, 0, 1. Which is 0, 1, 0, negative 1, 0, 0, 0, 0, 1. So punch that into your rotation z function, put in positive 90 and make sure you get this. And you can do this like, I mean, everyone has a little different syntax, but, well, I'm not even gonna do that. Okay, so now you can go Q, now that you have Q, you can go Q times our initial stress tensor, 5, 0, negative 1, 0, 10, 0, negative 1, 0, 2, and multiply that by Q transpose. And you should get what we figured out here, 10, 0, 0, 0, 5, 1, 0, 1, 2. That we're going to start with a state of stress that's all normal stresses. Let's say that there's 20 megapascals there, 10 here, and 15 here. And we're using our usual coordinate system. And we want to rotate the coordinate system counterclockwise 45 degrees about the z-axis. Okay, so if I redraw this stress cube, I'm going to draw it straight on. So I'm going to think of this as like z coming out, x and y. And I have 20 here, 10 here, and 15 here. And I'm going to rotate this now. If I'm rotating 45 degrees positive about the z-axis, I'm going to something like this, where my x-axis is this way, my y-axis is this way, and z is still out. Okay. And what kind of stresses are we going to get, you know? There's not really any way to, I mean, before we do it, there's not really any way to know, you know?
I mean, it'll be a mix, right?
It'll be a mix, that's right. We are going to have some shear stresses now.
I mean, like, if you wanted to, you could like just do the like trig and add it up, right? I don't know, like
Also with
No,
dot products, though.
you can't. You can't do it because, so I think like when you try to think it through, you tend to think about it as like coordinate system transformations of these vectors. But it's more than that. You're not just, so you're doing two things. You're coming up with the new traction vectors on new inclined faces, and then you're doing coordinate system transformations on those new vectors. So you could do it that way, you know, but it's two big steps.
yeah.
And it's really the same steps that this thing does all at once, you know. So our rotation matrix is going to be, so Q is going to be cosine of 45, sine of 45, 0, negative sine of 45, cosine of 45, 0, 0, 0, 1. And that comes out to be like 0.7071, 0.7071, 0, negative 0.7071, 0.7071, 0, 0, 0, 1. And now we're going to go Q times, our original matrix is 20, 0, 0, 0, negative 10, 0, 0, 0, negative 15, times Q transpose. And you get 5, negative 15, 0, negative 15, 5, 0, 0, 0, negative 15. And so up here on our X face, we have 5 in the positive X direction, 15 in the negative Y direction, That means on the y face, we have 15 this way. And we have another 5 this way. And then the z, the one we're rotating about, isn't changed because that face is still in the same direction. And then since I'm drawing it straight on, we can see all the faces here. So like this one really would have a 10 this way and a 20 this way. And over here we would have a 5 this way, a 5 this way, a 15 this way, and a 15 this way. Okay, so remember that if it was just as easy to draw these stress cubes in any configuration, we would always draw the stress cube corresponding to our new stress tensor rotated with the coordinate system. It just would be a nightmare to do, you know, and that's why we don't do it. But remember that the stress cube always has to match up with the coordinate system you're using. Okay. Okay, so the next thing we're going to talk about is principal stresses. I don't know how much we're going to get into this, but I can at least, I think I'll probably just set it up and that's kind of it. But principal stresses. You know, there's 2 words principal. There's like the Janet Jackson pleasure principle, and there's principal stress, and they're different words. And so this is not like
Like the person who runs the elementary school.
this is the person who runs the elementary school.
Okay.
That's the boss. That's why this is the boss stress. Okay.
Okay.
This is not the principle of what's a thermodynamics principle, like, you know what I mean? Those are, anyways, this is not like the pleasure principle. You should listen to that song, it's catchy. Done by Jimmy Jam and Terry Lewis. So how do you keep these straight? This is like an idea. This is like a big shot.
Isn't the principle of least action, isn't that a thing?
Yeah, probably. That's the idea.
Physics thing?
Yeah. Like philosophers talk about principles. Okay, and how do you remember? Because the principal of the school is your pal. That's how you remember which one is which. The big shot, you spell it P-A-L at the end. Okay. That's not part of this class. That's just extra information you get for free. So this is crazy. I'm about to tell you something that, why would this be true? For any stress tensor, come up with any stress tensor. There is a coordinate system where that transformed stress has only normal elements. Okay? That's weird, isn't it? You can make up any stress tensor that follows the rules of stress tensors, and somewhere there's a coordinate system that represents that same state, but everything is normals. I mean,
This is where eigenvectors are gonna come in.
yep, that's exactly right, exactly. And this, you can sort of see how it might happen with this example, how you go back and forth between normals and shears, you know. But that doesn't tell you that you could always find one with only normals. Okay, that's surprising, but wouldn't be particularly useful. But there's more. And so if you transform your stress, okay, wait, let me tell you the name. Sorry about that. Has only normal elements. So this is the principal stress tensor. So you don't have to worry about any shears. Everything's normal. And then this actually ends up being the more useful part. The greatest stress element in the principal stress tensor is the greatest stress element for any coordinate system okay, now that's getting a little weird, kind of amazing. And the minimum stress element in the principal stress tensor is the minimum stress element for any coordinate system. Now normal, I should have said normal here. So the greatest stress element in the principal stress tensor is the greatest normal stress element for any coordinate system. It actually ends up being the greatest stress element too, but
not in this other case.
it's true in this other case too. The minimum, but I sort of want to separate the shear and normal values. The minimum stress element in the principal stress tensor is the minimum normal stress element for any coordinate system.
So if there's any way to arrange your cube where there's gonna be a zero, that zero is gonna end up in your principal stress tensor.
Well, when I say this, I'm talking about, so minimum can be very negative or it can be very small positive. So you can go negatives or whatever, and greatest can be the smallest magnitude negative, or it can be the largest magnitude positive.
But you're talking, yeah, like kind of like absolute.
Yeah, like
Not absolute.
the technical meaning of minimum and maximum, you know, not absolute values. Okay, and I'm not done yet. If you rotate the principal coordinate system 45 degrees about the axis associated with the middle stress element. That new stress tensor contains a shear stress with the maximum absolute value of any coordinate system. Okay, so what's this for? What's the benefit of this? So we're starting to see, as we do coordinate system transformations, stress transformations, that there's not really anything particularly like intrinsic, physical about the values of the stress tensors, because those values are going to change if you choose a new coordinate system, okay? But if you could get a stress tensor and say, of all the coordinate systems, this is the biggest and the smallest the normal stresses can be, and you could say this is the biggest the absolute value of the shear stresses can be, now you're getting at something physical that you can use to really measure if something is going to break or not. Do you see what I mean? Do you see what I'm getting at? So these are these values, like, and so what I'm talking about is the maximum normal stress, the minimum normal stress, and the maximum absolute value shear stress are very useful in predicting damage. Okay, so that's kind of like the setup to the to this problem of principal stresses. One thing that's kind of interesting, like one way you see this immediately, like this 45-degree thing is kind of odd, but this is an interesting application of that 45-degree thing. Wood and bone are two things that they're not isometric, or they're not isotropic, I'm sorry. They have different behaviors in different directions. They're called orthotropic. So they have certain behavior, it's because of the grain, sort of, like they have certain behavior according to the grain one way, certain behavior according to the grain the other way. And they're both relatively brittle. And that stuff makes them susceptible to shear stresses. So if they break, it's usually going to be because of shear. Okay, so if you have a case of wood or bone breaking due to compression, so if the compression happens like this, you'll see this in car accidents where the driver's feet hit the front of the front of the car behind the pedals, and you'll see it in wood that's been hit too hard with a sledgehammer or whatever. The fracture pattern that you'll see is like this, and it's 45 degrees from the axis of compression. And that's because it doesn't fail in compression. It doesn't just compress too much this way. that compression corresponds to shear stresses along certain planes, and the first place that it breaks is along that plane where the shear stress is maximum.
And so in this case, you'd say the principal stress tensor is in line with the bone itself.
Well, so what you would say here is, well, yeah, remember the principal stress tensor is the one with only normal stresses. This doesn't have any, like in this coordinate system, the only stresses are this. And so it's already a principal stress. And so if you rotate that 45 degrees about the middle normal stress, which could be about X in this case, or it could be about Z because they're both the same, you get something like that. Yeah, kind of interesting. That's an application. So anyways, let's stop there, and we'll get into the calculations of principal stresses next time.